done some excellent work in introducing the neural network methods into the field of materials science, and he's going to give us some background on the neural network method today and some of the potential applications. So I'll hand over to you.
Thank you, John. So again, this is informal, so you can just stop me at any point and ask questions. For many, many years, I would say 25 years, I've worked on calculating microstructures, okay? And that's very, very nice. You can write nice papers and so on. But as I said yesterday, you know, the engineer is not interested so much in microstructures, but wants properties, okay? And mechanical properties in particular. And the kind of properties that are routinely required are illustrated here. So we need our material to absorb energy on fracture. So we have the Sharpe test, which is a quality control test, okay? Or if you want to use that property in design, then you do a fracture toughness test, K1C test, which is a material property, and then if you're constructing a particular structure, you can work out the fracture stress for that. Or most failures occur by fatigue, and we need to be able to say when something is going to fail by fatigue. Corrosion, many kinds of corrosion, stress corrosion, etc. And even the simple tensile test, once we go beyond the yield strength, we really have to measure the property rather than predict it. So these are what I call complex properties. In other words, we can measure them, okay? We can use them in design, we can interpret what's going on, but we cannot predict them. There is nobody in the whole world who can predict those properties if I give you a steel composition, a heat treatment, etc. For no material can you predict these properties. Okay, so I'm willing to be corrected if anybody can do this. Yeah? So we can measure them, characterize them, use them in design, and all of that is extremely useful. We can understand mechanisms, but we cannot predict those properties. So it's very dissatisfying. You can calculate microstructure, do a lot of work to do that, and then you're stuck. You know, you can't calculate the most important properties other than yield strength because we have nice dislocation theory and so forth. And that's not very satisfying at all. So, what do we do? Okay, so let me just summarize. Basically, all properties can be measured, and we have wonderful techniques to measure mechanical properties, and there's a whole science behind the measurement of properties, how much plasticity we have, and so forth. And those measurements are used to ensure that anything that we make is safe. Okay, so when we fly in the aircraft, we know there are cracks in there, but hopefully they haven't grown to a length where they will fracture rapidly. And we can use those measurements in control processes as well. But it is absolutely true to say that if I give you a comprehensive description of my material, that means the chemical composition, the heat treatment, the details of the microstructure, processing, you cannot predict any of those properties that I mentioned. Okay? So these are what I call complex properties, and we've got to tackle how to express them quantitatively and to use them in predictive design.
Harry, I'm just really concerned here. We're used to opening up an ISM handbook. We look up a type of steel, 4340, 9620, whatever, and it gives us a chemical composition, osmotizing parameters, quenching rates, and it gives you a yield strength.
Yes. Yeah.
But is it just a
measured?
Okay.
Yeah. That's you're absolutely right.
So what you're saying is that it's just because we're measuring it, we've been measuring it for the last whatever it is, that we've got this huge database.
We've got a huge database.
Okay.
But if that table didn't have properties, and I asked anybody in the world, challenged anybody in the world to give me a calculated value, they wouldn't be able to do it. Okay, the biggest names in mechanical metallurgy wouldn't be able to do it. So it isn't as yet possible to predict those properties. Even the simple hardness test. Okay, so there's a bright field optical micrograph and a dark field optical micrograph of a hardness indent, and we just take measurements of the diagonals and we work out a value of hardness. Even that is too complicated to predict because you have a lot of plasticity going on around the hardness indent. So even for that we cannot make predictions because, let me just show you a conservative list of variables which control hardness. So here you are. We've got a myriad of chemical elements, okay? Just like I said yesterday, even if the elements are in parts per million, they have a profound effect on properties. Thermomechanical processing, welding, of course, and any subsequent heat treatments. Now, how can you take account of all those parameters, each of which has an influence on hardness, and make a prediction? You will find equations in the literature which say hardness is equal to 20 times carbon plus so much times manganese and so much times, but they never include a comprehensive set of variables. So let me illustrate to you what happens when in such equations, or in any theory, we only try to study a few variables rather than all the variables that control the process. So here is a plot, okay? It's an X, Y plot, and I've got a series of points here, and they apparently look completely random, okay? I can't really tell you what this plot is about. Now, what I'm going to do, the reason why it looks like a random dispersion of points is that there are two variables which are missing, okay? We've only done experiments or we've modeled these points using two variables, whereas in fact they depend on four variables. There should be a z-axis out here and a time variable as well. Okay, so watch the screen carefully. I'm going to include these two variables, and immediately it will become clear what this is about. Okay, so it will happen quickly, so watch carefully. I'll start the So by including the z-axis and time, it immediately becomes clear what's happening. Okay? So again, this is a case where there is no point in simplifying things. You know, if you don't allow for all the variables that are controlling the process, then it simply isn't going to work. Okay? So we need a method which can deal with 180 variables happily, if necessary. Simplification just doesn't help with these complex properties. Okay, so I realize that, you know, whenever we have a large number of variables, we need to take account of that. So to summarize, okay, this isn't the end of the talk. I'm not giving up. There are, of course, very useful ways of expressing hardness. We can use equations in a limited domain, and we know that there are certain microstructures which are hard and others which are not. So an experienced metallurgist will be able to tell you just by looking at the microstructure that this is hard and this is soft. Okay? So his brain is able to perceive the entire relationship and tell you that it's hard and soft. And we ought to be able to capture that information quantitatively in a computer. Okay? All the experience that people have, we ought to be able to capture that. And in this day and age, we don't have a method for predicting hardness in general. Okay? So that's a sorry state of affairs, really. So the solution is, first of all, whenever we try to derive these regression equations, etc., we always tend to think linearly. So the hardness will be carbon plus so much manganese plus so much silicon, etc. And even when we don't, when we try to include the square of the carbon concentration, there will always be pluses. We need to get away from that and start to use nonlinear functions. We need to take account of very large numbers of variables. We need to treat uncertainties properly, and I'll explain that in more detail later. And as I said, there are volumes and volumes of data available. There's no way that we can absorb all those data. But maybe we can get a computer to absorb all those data. You know, if you have 180 variables, our mind simply can't think of what is doing what. Yeah? Or if it thinks, it can only give a qualitative answer. Okay, so let's start with empirical equations. So if I don't understand what is controlling the yield strength of a material, I might start by writing an equation like this, that the yield strength is a constant times another constant times the carbon concentration, a third constant times manganese, and so on. Okay. Simple linear regression. and I'll come back to this equation later. I go and I present that to my supervisor and says, you know, in my experience there is an interaction. These variables are not independent. You know, carbon and manganese influence each other. So I go and develop another equation where I multiply carbon by manganese. Now I don't know why I multiplied them together. There's no justification I have because I don't understand that interaction. Yeah? So again, I'm not really happy with this. And you know, if I have a bad dream, I might write an equation like this, yeah, with sine and hyperbolic tangents. So the point I'm trying to make is that when we don't understand the science, we don't really know what relationship we should be using. Okay? So any method that we develop really should not start with a relationship that we present, but it should discover the relationship itself. Okay? So that's what neural networks do. And to explain neural networks, you know, it's a fancy name. It sounds as if it works like the brain, but it's nothing like that at all. It's really quite a simple mathematical function, and nowhere near as complicated as what our brain does, you know. So it's a misnomer, but the terminology is established. Okay? So I'm going to start with the first equation here, simple linear regression, and express that equation using pictures instead of using this linear equation. Okay? So I have these inputs: carbon, the yield strength, and phosphorus content, and I want to predict the toughness. So in regression analysis, what I do is I take the carbon, I multiply it by a weight, a coefficient. Okay? Similarly, I take the phosphorus, multiply it by a coefficient, yield strength multiplied by a coefficient, chosen at random, add them up, and get a value of toughness which will be wrong because those coefficients were chosen randomly. But then I have an experimental value to compare against, so I can go back and modify those constants until I get a good fit. Okay? So that's exactly linear regression analysis. There's nothing new. But the way I've drawn it is the simplest possible neural network. That means we have a set of inputs which are called input nodes. This is the output node, the property that we are trying to predict. These are called weights, the coefficients in the equation. And this is where, you know, all the mathematics happens. That means we multiply carbon by a weight, multiply yield strength by a weight, phosphorus by another weight, add them all up, and that gives us the toughness. And this is what in neural network terminology is called the hidden unit, because really we are interested only in the inputs and the outputs very often. Okay? So that's a neural network representation of a linear regression equation. So we haven't done anything new as yet except expressed it pictorially. Now to make it nonlinear, instead of taking carbon, multiplying it by a weight, and then adding it to the others, we take carbon multiplied by a weight and take its hyperbolic tangent function. Okay? Now hyperbolic tangent looks like this. Okay? And depending on the value of that weight, it can be almost a straight line, it can be very gentle, or it can be very steep. So the reason why we are using this hyperbolic tangent function is that it's very, very flexible. Depending on that coefficient that we put before the carbon, the slope of this function and shape can change drastically. Okay? So we made it non-linear because there's no reason in nature why things should be linear. We still have a problem, is that this may not be sufficiently non-linear. So for example, if I'm modeling the yield strength as a function of carbon, yes, it will increase, and it might even flatten out because it comes out of solid solution. But at some point we are going to precipitate graphite and the relationship might change completely. Okay? So this function, once I've defined it, is the same everywhere. What I need is for this to be even more non-linear. So why don't I add another hyperbolic tangent, and then I've got a function which is even more non-linear. I can carry that on, keep on adding these hyperbolic tangents until I get a sufficiently complicated function. Okay? And that in neural network terminology is the number of hyperbolic tangents that we add is the number of hidden units. So here I not only multiply carbon by one weight and take the hyperbolic tangent, but I multiply it by another weight and take another hyperbolic tangent, and that gives me a more complicated shape to the function. Okay. Let me illustrate how complicated I can make this function. need to open this. Yeah. Okay, so here is a very simple neural network where I've got 4 hyperbolic tangents. Okay, so I'm modeling Z, and I've got 2 variables, x and y. Okay, and the weight here is the n, w. Okay, and by varying this weight, okay, I'm just adding 4 hyperbolic tangents. You'll see this surface will do really, I can change its shape so much. Okay, so all I'm doing there is varying the value of n, and you can see how flexible this function is. Whatever nonlinearity I have in my data, I'll be able to capture it. And this is a very, very simple combination of just 4 hyperbolic tangents. Okay? So this is the reason for using hyperbolic tangents, is that they are very flexible functions. We can change the shape. So whatever the complexity of our problem, we can model it. And we can continue adding hyperbolic tangents until it's sufficiently accurate to model the problem. Okay? Okay, so this is again our representation of the hyperbolic tangent of the neural network, and mathematically it's very simple. Yeah? You can't possibly represent the brain. It's just too simple an equation to represent the brain. There's no black box here. You see, some people say neural networks are black box, but it's a well-defined mathematical function. You put in the same output, you get exactly the same. If you put in the same input, you get exactly the same output. Okay? So here is the combination of as many hyperbolic tangent functions as we want to make it a nonlinear surface of arbitrary complexity. And this goes into this equation, and we have our output value. And therefore we can produce very nonlinear functions. Okay, so we've got around the problem of making things nonlinear and arbitrarily nonlinear. We can make it as complicated as we want. So if our property is a very complicated function, we now have a powerful bit of mathematics which will allow us to capture that complexity. There is a problem though with nonlinear functions, and that's illustrated over here. Okay? So I have a set of experimental data, okay, and I know that if I repeat the experiment I get some scatter. Okay? But if I have a very complex mathematical function, I can make it pass through every single point with 0 error. Yeah? Now, is that right or is that wrong? I don't know. If I don't understand the science, I don't know whether I should really be fitting a straight line through here, or is this function the correct function? Yeah? So whatever the complexity, I can produce the mathematical function which will pass through every single set of points. Okay? Even if you give me a random set of points, I could create a neural network model which will pass through every single one of those points. So this is a major, major problem. Okay? That what we are doing, possibly, we don't know that. What we are doing is that we might be fitting noise. It may not be justified to have a function of this shape. Okay? So how do we get around this problem? Well, what we do is we take our data and we split it into 2 parts. Okay? We only use one part to create the model and the other part to test it. So here are 3 plots. The black data are used to create the model, and the white data are never shown to the model when we are creating it. Okay? So you can see here the model is too simple, so the error associated with the training data, the black data, is going to be large because look, we have all these discrepancies here. And similarly, the error associated with the test data, which have never been seen by the model, is large because we simply don't have enough complexity here to model the shape of the data. So we will have a large test error and a large training error if our model is too simple. Okay? Supposing we now make it extremely complicated so that it passes through every single point in the training data set. Okay? And we get a function which looks like this. Then it will generalize badly on the test data. So it's predicting this point very badly because it's undergoing this sharp curvature here. And similarly, this point is far away from there. So we are on this regime where the trailing error has gone to more or less 0, but the test error is large because the function is behaving badly between the points. In some region of complexity, we will find that we get roughly the same sort of error for the test and the training data. And that is how we get rid of the overfitting problem, is that we use only half the data to create the model and the other half to test how it behaves in regions where we haven't used data to train the model. Okay, is everybody happy with that?
But
Yes.
can't you have data on this? I mean, you can, that process can be pushed on forever.
Yes. So now you're talking about extrapolation beyond the data. Yeah?
Because you're saying once you start hiding the data, there's always data that you could be theoretically be gathering that you could add to your model.
Yeah. So the more data you have, the better the model will be.
Okay.
Yeah.
How do you split the data on
We
these
do-
two groups? So it's any special rules, for example, that you select the data which goes to the first group and the data which goes to the...
Random splitting is the
Random.
best
Okay.
because then you cover every domain in the input space.
Oh.
Okay, so let's assume that we can solve the overfitting problem. Okay. Then there is another problem which you have just raised, and therefore you have to answer this question. Okay. I've got this set of data here. What will be the next two numbers?
Well,
Excellent.
that's
There you go. 10 out of 10. Okay.
good.
Next two numbers 10, 12. Okay. So we've created a model here, which is a linear model which has predicted the next two set of numbers, and we regard this as our experimental data. Okay. But I can find another equation which will exactly represent 2, 4, 6, and 8, but give me different answers here.
Yeah.
And that equation is here. If I put in a 2 for x into this, I will get a 4. If I put 4, I will get 6 exactly. If I put 6, I'll get exactly 8. But if I put 8, I'll get 8.91, and so on. Yeah? Now, we don't know which one is correct because they both exactly represent the experimental data.
So,
Yeah.
mhm.
So this is what I call modeling uncertainty. Okay? So if I plot those two functions, they extrapolate completely differently. Right? And we have to take account of this error, this uncertainty. When we make predictions using the neural network, we have to recognize that there are certain regions where different models will get different predictions, and that indicates that you have to be careful in using the predictions. It doesn't necessarily mean that there's anything wrong, it just means that you have to use your science, etc., to decide on what you're going to accept here. Okay? So here I would give a large uncertainty, here I would give a small modeling uncertainty, and that would diminish as I go towards this, towards the experimental domain, if you like. So the danger of extrapolation or interpolation is expressed by working out this error. We would effectively try out an infinite number of functions to fit the data. If they behave in the same way when you extrapolate, then the uncertainty is small. But if they behave very differently, then the uncertainty is large. So if I show you the next slide, this is the domain where we have experimental data. Here we have three models fitted to the experimental data. They behave differently here. So I would have a large uncertainty here, small uncertainty here, etc. And then you have to use your scientific judgment that have I made a correct prediction or not? Because we don't know which of these models might be correct. Okay? So that's what we call the Bayesian uncertainty of modeling. And that's why the error bars change according to where you do the calculation. Whereas in linear regression, you can specify the range over which your data exists simply by tabulating the minimum and maximum values. That's no longer possible in a nonlinear function, because say if I have a range of carbon concentration from point 1 to point 2 over here, I might have a different range where the manganese concentration is different. Okay? So it's impossible to say that I've created a model within this domain of experimental data, because the range will vary according to where you do the calculation, and this is a method which tells you how dangerous a territory you are in. So this is extremely important, and not all neural networks do this. Okay, so this particular technique that we are using, due to David Mackay, gives you this uncertainty of modeling in addition to noise in the experimental data. Noise is when you repeat an experiment and you get a different answer because some variable is missing. Okay. And then you have to use your scientific judgment to see whether it's reasonable or not. So I showed you these calculations yesterday, and these are the uncertainties of modeling. Whenever you're making something new, you will get a large uncertainty. But if you notice that the trend, as a function of nickel, is justified because you know from metallurgy that nickel has a big effect on the coarsening rate of precipitates, then I would be happy to accept this result, even if the uncertainty is very large. But if I get a result, which, as I increase the temperature, the rupture stress goes up, I would worry about that. Yeah. So we've applied this model, the neural network method, to very many complex properties, all of the properties that are listed there. And of course it has many general applications in all of the sciences. Yeah? So there's a review paper which we'll put on that space that we've created, where you can look at hundreds and hundreds of applications in all aspects of science, sociology, everything of the neural network method, because this is a completely general method. You can make this very physical as well, because the inputs that you choose, can be microstructure, the fractions of different carbides, etc. And then this slide which I showed you yesterday come from a neural network model in which we are including the strengthening components due to solid solution, the carbides, etc., etc. So we can get a non-linear factorization of the strength. Okay? And we can say that, look, here, this much of the strength comes from precipitates, okay? From the microstructure, from solid solution strengthening, and how that changes with temperature. So this kind of information is extremely valuable from the point of designing alloys. And I'll show you again this example, and there are many more I can show you. So this is remarkable. These were presented at a conference in London, and the calculations fit the data so well. You could have avoided 40,000 hours of experimentation. And the uncertainties are very large because we are working with a new alloy that was developed by Nippon Steel. Nevertheless, the predictions are good because the trends of the model are correct. And similarly, here's another set of data. I could go on and show you cases of success and of failure. So I'm going to show you a case of failure now because that's more interesting. This is a project which over a period of 3 years we had to design a welding electrode for a particular need in a power station. So the need was identified by market really, that we needed a welded rotor instead of a continuous rotor. Because in one part of the rotor we needed toughness, in another part we needed creep strength, and the two steels were incompatible. So we created a whole set of models, including microstructure, tempering, working with industry. And the idea was within 3 years to come up with a marketable product. Okay? So it wasn't a case where you could try out many different alloys and so forth, because testing takes a long time. Yeah? So using a combination of all those models, we made some manual metal arc electrodes purely by calculation. These were the engineering requirements, and we met them on the very first go. Okay, so all the measured properties fall above the design requirements which were given by the engineers. Now, being in a university, the idea here was that they would do a post-weld heat treatment which was 650 degrees centigrade for 8 hours. Yeah? So we've met all the conditions that were specified. but we decided to do some more experiments, and it's always a bad thing to do this. And you can see that when we went to 700 degrees centigrade tempering, huge discrepancy between the prediction and the measurements. So something is very wrong here. And the discrepancy seems to increase as we go to higher and higher tempering temperatures. So what is wrong? Well, the microstructure was supposed to be bainitic, and sure enough, in the as welded condition, without going into details, this is a bainitic microstructure, tempering at 600 degrees centigrade, all is well, 650 degrees, all is well. If I show you now what happens when we temper at 700 degrees centigrade, you get these large regions which are recrystallized. So the strength is actually very low compared with what we expect. So what I'm saying is that the neural network helped us to identify a region in which we needed to do an experiment. Yeah? That is a really important thing that you get from the neural network, because you have so many variables and you don't really know where you need to do an experiment. But here there was clear disagreement, and we did the experiment, we found the reason, added a little bit of vanadium to pin the boundaries, and the problem disappeared. And we
Why
obtained...
is it done in the recrystallization is in bands? Is it
Yeah.
some segregation effect or?
Yeah, you see, this is a manual metal arc weld, and because a human being is not completely steady, the solidification rate changes in different positions, and therefore you get solute banding. Okay. And therefore we have recrystallization in the solid depleted regions of the weld. Now, this is the final commercial product then, and that is the second iteration, if you like. This was the first iteration because it's easier to make manual metal arc electrodes for testing purposes than continuous electrodes. Okay. Now, exactly the same method has been used by all of these companies for different problems. So Siemens was the company for which we did the development of this electrode. Mitsui Babcock have made another welding electrode which is like a 2 1/4 chrome moly steel, but it doesn't require any post-weld heat treatment because they're using it to make boilers. And the boilers, it's not possible to really give a huge post-weld heat treatment to. Nippon Steel had a requirement to increase the fire resistance of welding alloys that they use for buildings. And they used exactly the same software in the first iteration to get an increment of strength that they needed. And ABB are not really interested in metallurgy, but they are interested in making robots. And you know that lasers are becoming much cheaper. Yeah? So diode lasers are coming in, and the normal robots that are used for making resistant spot welds are really huge, and they have clamping forces and so forth. Whereas if you had a laser, you could just pipe the laser beam with an optical fiber, use a small, very agile robot to do the work. But in order to sell this, they had to do the metallurgy behind it. In other words, to make sure that the properties you get from the welds made with lasers are the correct properties, and they used our models to do that. Okay, so they now sell a package of a robot, a laser, and software which gets the right conditions for doing the welding. Now, steels, people have tried extremely hard, ferritic steels, to get them to operate at a temperature of 650 degrees centigrade. Even we might succeed in doing that. 650 degrees centigrade for 25 years with a stress of 100 megapascals. Right now, the best we can do is 620 degrees centigrade, but there are huge research programs to go to 650 degrees, because ferritic steels are absolutely wonderful. They have a low thermal expansion coefficient, okay, high thermal conductivity. So, when you get temperature fluctuations, you don't get thermal fatigue, etc. Whereas austenitic steels have the opposite, and they fracture very quickly in the power station scenario. But in Europe, we want to go to even higher temperatures, steam temperatures of 700 or 750 degrees centigrade, because imagine the gains in thermodynamic efficiency. Yeah? For the same amount of coal, you could really get much more electricity. So we have a target by, I think, 2020 to cut CO2 emissions by 60% even though energy consumption will continue going up. So 60% to last year's consumption figures. And we can do it, yeah, because there are a number of technologies which will help to do that. One is to increase the steam temperature. And strangely enough, Denmark is the country which leads in increasing steam temperatures, okay? Because they have green laws, you know, which say that you must have this much efficiency in power generation. Okay? So, unfortunately, ferritic steels will not be able to go to 700 degrees centigrade. Probably not. Never say never, but probably not. Now, nickel has almost the same thermal expansion coefficient as ferritic steels. Of course, it's a lot more expensive. You know, if you take a turbine blade from a jet engine, it's worth its weight in silver. Okay? You cannot possibly make a power station out of an alloy which is used in jet engines, even though it has remarkable properties. You know, it operates at 1,000 degrees centigrade without any trouble. So what we did was we took an aero engine alloy, removed all the expensive things that they put into it. So we are now going backwards, because we want to use this at a lower temperature. We don't need things like rhenium and so forth, that all kinds of exotic elements that are added in aero engine alloys. And we did all this work using, you know, microstructure models and neural network models, this time for nickel alloys. And we came up with this chemical composition. Okay? And this was again in discussion with industry, because we don't really want iron in this alloy because it deteriorates the creep properties. But they said that if they can use scrap material to make the alloy, then it reduces the price enormously. Okay? So we've got iron because they would prefer to use ferrochrome instead of chrome. Similarly, we don't really want silicon, but they claim that for casting properties they need silicon. So we came up with this design of alloy, and of course there's a microstructure issue, I won't go into that. And this was our prediction, and these are the actual properties that we got from it, okay, in the first iteration. Now, I've shown you that, you know, the neural network method is actually quite a simple method, but it's very, very powerful in dealing with complex properties, and you combine it with microstructure models and physical metallurgy experience, and you can really develop new materials very, not very rapidly, but more rapidly than you would normally do. So let me just show you some of the work that we've been doing here with John Francis using this method. Okay? So there is a problem in welding power station materials, in that if this is a weld metal, the weld metal is hard, and the parent metal is also hard, but you end up with a zone somewhere around here which is soft, okay, because that's a tempered zone. So you can see here we've got a soft region. So when there is a stress applied, you tend to focus the strain in this region, and you get failure over here, and that's known as type 4 cracking. And that failure is possibly the most common method of failure in power stations. Okay? And as you go to these high chrome steels and so forth, this problem becomes worse. And that's illustrated in these are just taken from the literature. So this is a case where it's failed in this inclined manner. You can see the creep specimen has failed by a type 4 mechanism, whereas this is how it would normally happen if it failed in the parent plate. Okay? Now there is no method of predicting the failure stress. Okay? So let's assume that for the parent plate we can predict the creep rupture strength, because I've already shown you models where we can do the creep rupture strength as a function of, you know, something like 50 variables. Okay? How do we decide what's going to happen here? Well, we don't know how much strain we are going to concentrate in this region. Okay? And the effect of that concentration of strain is to make it fail at a lower stress than if this was just a homogeneous piece of material. Now there are data in the literature in which people have done cross-weld tests and you get type 4 failure, that means over here. So they've reported all the experimental data, the heat treatments, the chemical compositions, and the rupture stress. When you get type 4 failure and when you get failure in the parent. For the parent, we ought to be able to predict things accurately. For this, we should find a shortfall. That means the stress that we predict will be higher than the actual stress at which fracture happens. And just yesterday, we did this analysis, and sure enough, so these are all calculations now. This is the experimentally measured failure stress for type 4 cracking. Just focus on the blue points. And this is what we would predict if this was a homogeneous steel. Okay? So you can see that the actual failure stress is always lower than what we predict. Okay? So supposing that we want to predict the stress for failure for type 4 cracking, I take these data and I draw a line through them, then I have an offset here. So if I just use my model for predicting the plate creep rupture strength and then subtract this much, then I've got the stress rupture for type 4 cracking for the first time ever. Without doing any experiment, we might be able to. I'm sort of being very optimistic because John has very many more data which we need to plot here, but we haven't had time to do the calculations. But let's assume that the trend is still obeyed when we put in all those data. If we can simply offset the predicted strength of the plate to model type 4 cracking, then that will be a very powerful method because we don't have restrictions on the chemical composition of the steel for which we can model the creep strength. So whatever steel you come up with, we should be able to predict the type 4 cracking. And just to confirm that if we get failure in the parent plate, then there shouldn't be this offset. Here's the one point, okay, which we've plotted so far, where there is no offset here. So this was failure in the parent plate. So our feeling is that when we take the large amount of data that John has accumulated, whenever failure happens in the parent, the points will fall on this line. And whenever it's type 4 cracking, we'll be able to define an offset here. Okay, that's all I have to say. Except one thing, that this is a completely general method. You could apply it to any material or any problem that you have. So just to give you an idea, the New York police have a neural network model to predict which policeman is going to become corrupt. Yeah? So they've looked at all the case histories of corrupt policemen and put in parameters, and they claim that they are able to predict which policeman is likely to become corrupt. Okay, so I'll be happy to answer any more questions.
I just wonder in this case if there's an opportunity to, as well as using experimental data to train the network, can you use some sort of mechanistic understanding to make it even better?
That's an excellent point, you see, because some of these mechanistic models that we have take a huge amount of computer time to run. So supposing you want to control the whirlpool shape, you have equipment which can monitor the whirlpool and adjust the current, etc. to get the right shape. Yeah? Now there are computer models for a whirlpool shape, but they might take several weeks to reach an answer. So what you could do is you could run those computer models, get the output from that, then train a neural network, which once it's trained will take milliseconds to run, so you can use it for online control. Yeah? And helicopter engines generate a particular vibration spectrum, which is modeled by a neural network, and as soon as it deviates from that, you've got to land quickly. So that is in commercial practice.
What about for things like the rupture stress or toughness prediction?
Yeah.
Are there models out there that people go in detail and calculate those sort of things as well?
Toughness hasn't been done, but the creep rupture strength, I showed you, that M23C6 is contributing so much and so on. So what we've done is we've taken thermodynamics. For each steel, we calculate the fractions of phases, and the compositions of phases, so that we can put solid solution strengthening terms and so forth. And we use those as inputs to model everything else. So instead of using, say, the raw chemical composition and the heat treatment as inputs, we use the microstructure as inputs to create the model.
Sure.
Is that what you meant, or?
Partly, I think. I guess I'm also thinking of the question of whether there's anyone sitting down who's trying to write a detailed model that can take a microstructure and tell you and spit out a number for rupture strength.
No, there's nobody that I know. I don't think that it's. I mean, there are just too many variables and too many unknown bits of science.
Yeah.
Would you also say that, wouldn't it also depend, I mean, we use the word microstructure, and I think it can mean quite a lot of things. You know, microstructure could be what we could look at under whatever analysis we want to look at, optical, SCM, or whatever. Or you could say that microstructure is the volume fractions of all the different phases that we can calculate into something. But from a practical point of view, there has to be I mean, we can look at a sample, we can prepare it and look at it. There's a discrepancy with what we see or what we interpret to what this actually is. And then there's also there's nothing that then links that to mechanical properties.
Yes. No, you're right. You're right. So supposing we just do volume fractions and particle sizes, then the crystallographic information is missing. You know, and a crack, when it propagates between grains, really does follow the crystallography. Yeah. You see, it is just too complicated a problem. Yeah.
Oh, yeah.
Yeah. I think.
No, it was a question about the toughness, but you answered this question. I think that it's probably is too complicated.
Yeah. I mean, we study
predict-
micromechanisms,
Yes.
but we don't make it quantitative.
If you had to train this software for a new process or new application, what are the parameters needed to?
You need data, okay? And you need to take account of as many variables as possible. Now, you can make your list of variables very ambitious, in which case your data set will decrease in size, okay? Yeah, so you have to reach some sort of a compromise that you need a large data set, okay? You don't have to specify how large to begin with, but your uncertainties, modeling uncertainties, become large if your data set is small. So you will automatically know that you need more or less data. Yeah? So you identify the variables for which you can get the data, accumulate a sufficiently large data set, and then create the model. Yeah.
But that would also imply that you would need to be completely aware of all the variables in it.
Yeah, but you know, as metallurgists, I think we are, you know.
Yeah.
We know, we have the feeling that, you know, hydrogen is not good, and so on and so on.
In most
yeah?
cases it's not, yes.
But the problem is when people publish papers, they don't report everything that you need to know.
You're absolutely right.
Have this been used in like development of electrodes where nitrogen and hydrogen has been like eliminated?
Yeah.
Or some kind of composition that can be reached which take care of.
If I show you just in the Crete model, you know, the variables that are included. Let me just see, where is it going to be? And again, if you go onto my website, you can download all these models. So look, this is the list of variables, just for the Crete model. Okay? And it goes on a bit further. And nitrogen is one of those. In the case of the electrodes, there's many more. You know, oxygen and so forth. Yeah, oxide has a big influence. And we've got virtually every property of structural steel weld that you can predict. And this software is routinely being used by lots and lots of companies.
Harry, have you found that it's common that through doing a neural network analysis, you get some physical insight? Like there was an example you gave there of the recrystallization, but you might attempt to tackle a problem with no physical appreciation of what's going on, and then is this a common thing?
It is very common, and let me see if I can dig out a particular presentation. And show you, people think that we can improve toughness by adding nickel to a ferritic steel. You find it in many textbooks and so forth. So we were asked to develop a welding consumable for submarines, which can be used without any preheat and so forth. That's a really tall order. Okay. So of course we thought, okay, the first thing to do is to increase the nickel concentration. And after 3 years of work, it didn't actually succeed until we did a neural network model. Yeah. So what this shows is a plot of the energy absorbed at minus 60 degrees centigrade. Okay? Calculated using a neural network. And we are plotting manganese along here and nickel along here. And look, as I increase the nickel concentration, the toughness actually decreases. Nickel only improves the toughness when we go to a low concentration of manganese. So we were able to identify immediately a domain where we should be able to get improvements in toughness. Okay? Now, of course, this doesn't tell you why this effect works. Yeah? It just tells you that nickel will work at a low manganese concentration. So we did these experiments. Now you have in this laboratory you have a hardness tester which sort of maps a complete weld. Yeah? And these experiments are done using that hardness tester. And what you see here is hardness contours. Notice how remarkably they reflect the microstructure. Yeah? There's nothing here except hardness being plotted. And what happens when you have a high manganese and high nickel concentration is that you get these very hard spots inside the weld. Yeah, because the hardenability in those regions is very high because of chemical segregation. When I reduce the manganese concentration and have a high nickel concentration, I get that. And we can show using thermodynamics that the segregation levels here are much less than over here. So that's a physical insight which comes from the neural network modeling. And it's simply that, as human beings, when we see that nickel has increased the toughness in a particular alloy, we assume that it will do it for everything else,
Okay. Just one more question. Something that if you say you're using neural networks to solve one of your problems, people often say, "Oh, neural networks is not new. That it's been around for quite some time."
More than 50 years, yeah.
Yeah. So, in your view, what is the principal benefit of using the approach that David McKay has
Exactly.
developed?
So that is not new. That is new,
Yep.
and it's that Bayesian uncertainty of modeling. Yeah?
Okay.
Because if your neural network model doesn't give you an appreciation of how far you are extrapolating, then that is very dangerous. Yeah, it's very dangerous. So almost all other techniques do not give you that.
Okay.
In the case of that nickel one on the previous slide, could you summarise the benefits of the neural network as being almost a visualization tool?
Pattern recognition.
Yeah,
Yes.
because you probably got, I guess, data that shows cases with high manganese and high nickel where you've got the unexpected trend,
That's
but
right.
it's hidden away in your filing cabinet.
Well, you see, a slight modification to what you
Sure.
just said is that because there are 50 variables,
Yeah.
you would never be able to deduce this effect by looking at individual papers, because what it has done is separated out the effects of nickel and manganese. Do you think?
Yeah, with
You
everything
may-
else constant.
Yeah,
Which
exactly.
you couldn't do. Yeah.
So you can do experiments using the neural network which you couldn't even do in principle
Yeah, gotcha.
experiment with real experiments.
If there's no more questions, thank Harry for the
Okay.
presentation.